Assalamu alaikum warahmatullah. Now we move on to linear mappings. A mapping actually is a general function. So we talk in a bit of abstraction regarding the mappings. So a mapping uh, takes a takes you from one set to another set, or from one space to another space, generally speaking. Okay. Now we will add some properties on those mappings. Now if the mapping is linear, meaning it satisfies those two properties, additive, so the mapping is additive, and homogeneous, meaning that you can take out the scalar out of the mapping. In this case the mapping is called linear or homomorphic, or this is a homomorphism. Okay, so we can combine those two properties in this single line. Okay, now the set V is called the domain, and set or space W is called the codomain. Right. So again, we would like to define a few properties of such mappings. Now a mapping is injective if for all x and y belonging to the domain V, the mapping of x equals the mapping of y if x and y are equal. This is called one-to-one mapping. Okay. A mapping if surjective is mapped to the whole set of the codomain W. So this is called surjective mapping. Bijective mapping if it's injective and surjective. Okay. So we have a look at figure 1.4 and have a small example for them. So we have, let's say this is the domain X, this is the domain, and the codomain here. Again, X and Y are the domain and codomain for all the examples. So here this mapping is injective, meaning every element in X, so meaning all X in capital X, for all X in capital X, there's a single image for the elements. Okay, but this is not surjective, meaning the point C here cannot be reached by any point in X. So this is not a surjective mapping, hence it's not an injective mapping. Okay. Also, if it's not injective, meaning that it's not bijective as well. This mapping is very nice. So it's one-to-one mapping, right? You can see it, and all the points in Y are reached by points in X. So it's injective, surjective, hence it's bijective. Okay. Now this mapping, it is surjective, meaning all the points here can be reached by points in X, but if you look at point 3 and 4, they have the same image, point C. This means that it's not injective, hence it's not bijective. So it is surjective but not injective, and hence it's not bijective. Okay. This one, it's not one-to-one, meaning so it's not injective, and you have point A here that's not reached by any point in X, so it's not surjective. Okay. Okay, so those are the main properties. Okay, so we have again another set of properties here. Isomorphism if it's homomorphic or linear and bijective. Endomorphism if the map is linear, the mapping, and you map V to W, so v to itself. Okay, so when you map v to v, the same vector space or set in general, it is called endomorphism. Okay, example. So we have, look here at this definition. So the mapping name is phi. The domain is r squared. The codomain is the complex set of numbers. So phi of x, so here x belongs to r squared, of course, right? Is taken from r squared to the complex numbers. So x now, the vector x becomes a complex number. This is homomorphism. It's a linear mapping. Okay, how is it linear? We can check the two properties, additive and homogeneity. Okay, so if we take two vectors x and y belonging to r squared, of course, the output would be in this form, right? So in this case, this is actually the mapping xy, and this is the mapping of what? y1, y2. Okay, and it's very straightforward to see that this mapping is homogeneous. You can multiply here by lambda, then you can take it out, and this is actually the same mapping, right? Phi. It is surjective since any complex number can be represented by a vector. Okay, it's not always easy to see that the mapping is surjective, but in this case it's somehow easy. Okay, it is also injective because it's a one-to-one mapping, hence the mapping is bijective because it's injective and surjective. And it is isomorphism mapping based on the definition. Okay, we have some properties of the mappings. So if phi takes you from w to v and psi takes you from v to x, both of them are linear mappings, so you can have the composition. So phi compose psi will take you from w all the way to x. It's very simple to say. Now if the mapping is isomorphic, linear and injective, so we can define phi inverse that will take you from v back to w. Okay, and this isomorphic map, so if phi is isomorphic, so is phi psi, phi inverse. Okay, now if both mappings are linear, then their addition and multiplication, scale multiplication, are linear too. So those are simple, nice properties. Okay, we talked about the general mapping. What we are interested in is the matrix representation of linear mapping, or linear mappings, which is done by multiplication of matrices, by matrices. Okay, so here we can define the mapping from v to w using the basis set b, okay, and some vectors c. Then we can define the mapping of a single basis as this linear combination of the vectors, right? So this is a unique mapping with respect to the set of vector c, right? Now recall, now this can be represented as a matrix, right? So the matrix would have m rows, which is the number of columns here, or number of elements in C, and n columns, which is the number of basis vectors, right? So we can stack them beside each other, right? So let's take an example here. We have this A, okay? Now we use A to represent linear mappings. Now the mapping name is phi. So the first thing in defining mappings is to define the domain and the codomain. So the name of the mapping is phi. It will take you from the domain r to the power 4 to r to the power 5, r5. Okay, and we denote it by this. So x here belongs to r to the power 4, right? And ax, which is here, depends to the codomain r to the power 5. So this is very important. From this you can infer, you can guess the size of the matrix A. A, it will get multiplied by a vector in R4. So the columns of A should equal the rows of X. X lives in R4. So it has 4 elements, hence it has 4 rows. So A must have 4, sorry, A, yeah, must have 4 columns. Okay, the output would live in R5, meaning it will give you vector in R5. R5 meaning it has 5 elements, hence it has 5 rows. So this is the dimension of A. So this is very important to know. Okay, now we studied this matrix before in a previous example. Now we know that columns 1, 2 and 4 are independent. Okay, so this matrix is, now what we need to find is that, is this matrix injective, homomorphic, isomorphic, endomorphic or automorphic? Okay, we use this fact, right, and this fact as well. We have done that in a different video regarding this example, so we'll move on. Okay, linear mappings have many practical applications. One of them is a transformation, geometric transformation, such as rotation and stretching, as you can see here. So if we have this original set of data, we can rotate it by 45 degrees using this matrix, cosine pi over 4, which is 45 degrees, or you can rotate it by any angle you wish. Okay, you can stretch it using A2 right here by 2, or you can stretch it in different directions as in A3. So A3 is a general mapping, so you can think of a matrix as a transformation, a geometric transformation in different directions. Okay, now we move on to discussing images and kernels of mapping, especially linear mappings. Okay, so let's talk about the simple one first. The image is the output, is the range of the mapping. Okay, whereas the kernel is a null space of the mapping, meaning the null space and the range, they are defined differently. Okay, the range is the output of the mapping, the result of the mapping here. So meaning that if I have this mapping phi that takes you from V to W, so the image of phi is all the vectors in W such that there exists a vector V in W with this mapping. Okay, so I take any vector V, small v, in the set V, and it will be transformed, it will be mapped to vector W and set capital W. Okay, so again the range is the output of the mapping. Contrastly, the kernel is the input of the mapping. Which input? Is the input that will give you the all zero vector, the all zero vector. Okay, so in matrix format, when we talk about matrices, the image is the column space of the matrix and the kernel is the null space of the matrix. So here's a graphical representation. See, so here's the domain and the codomain. Those are the sets, and we have the mapping phi that takes you from V to W. This mapping takes you, if you look, this V takes you to from the yellow part here to the yellow part here. So you can directly say that this mapping is not surjective, right? Surjective, because we have points here that are not reached by the mapping. Okay, so here's the image, right? Now the kernel of the mapping is this set that is mapped to the all zero vector. Okay, now if the kernel of the mapping is more than the all zero vector, this means the mapping is not one-to-one. Why? Because, okay, we know that 0 get maps to 0, but maybe some other point here get maps to 0. So you have 2 points with the same image, meaning that this mapping is not one-to-one, so it's not injective mapping. Okay, so if you see a null space that is not trivial, meaning that has more elements than the all zero vector, this is indication that the mapping is not injective or one-to-one. Okay, example. So we have this mapping now. It will take you from R4, meaning X is in R4, to R2. So the output is AX is in R2, and the matrix must be 2 by 4, as we said earlier. We need to find the image and the kernel of the mapping. Okay, now note that those two are subspaces. Okay, those two are subspaces. Subspaces of who? Subspaces of who? Okay, as we said earlier, the column space of A or the image of phi, same thing. Those two, they belong to what? They are subspaces of who? Of this one, of R squared. Whereas the null space or the kernel phi and the null space of A, both of them, they are a subspace of who? Of the domain of R4. Okay, this is very important. Okay, so okay, as we said earlier, the image of phi is the span of the vectors. Now we need to make a distinction here. So this span of the vectors of the columns. The vectors are the columns of the matrix A. Okay, this is the same as span of the basis vectors, which are who? Which are the first two columns here, as we see. So those two sets, they are identical. So this is, as we said, this is the minimalistic set, the minimal basis set, right? This is a span, a set of points that are reached by the matrix or by the mapping phi. Okay, now, so this is the image, or as we say, the column space of A. Now, the null space is the solution to this equation. How do we do it? We can find it in many forms. There's many ways to find the null space. Okay, one of them is to find the row reduced echelon form. Okay, so as we said earlier, we can say that the first two columns are independent and the third and fourth columns are not. So what we do is that we represent the dependent columns A3 and A4 by the independent columns. So you can do it by just checking the matrix here. You say, okay, A3, which is this column, is actually A2 multiplied by minus 1/2, right? A4, on the other hand, here we have two elements, so we multiply A1 by 1 and A2 by minus 1/2, right? So we get A4. Now we put those two in an equation format like this, and then we take their coefficients, and we don't forget all the vectors, right? So this is minus 1, right? The coefficient of A, minus 1/2 here. Then we have 0 for A3 and 1 for A4. So the vector is the coefficients in the first equation, and the same thing here, right? So you have 0 for A1, 1/2 for A2, 1 for A3, and 0 for A4. Now those two vectors, they are the basis of the null space. So the kernel of the mapping, or the null space of A, is spanned by those two vectors. Okay, you can find those two vectors by using the -1 trick mentioned in the book.